Good evening, everyone. Speaker for this session is today's session is Dr. Mohammad Arifuddin Sohail. Sir has already joined the meeting. We were waiting for the participants to join. We'll start off. It is my absolute honor to introduce our esteemed speaker for this session, Dr. Mohammad Arifuddin Sohail, a distinguished professional in the field of electronics and communication engineering. Dr. Mohammad Arifuddin Sohail is working as Head of Research and Development at Advanced Communication and Electronic Systems, Saudi Arabia for the last 2 years. Prior to this, Dr. Arif was the Professor and Head of Department of Electronics and Communication Engineering at Mufakhamja College of Engineering and Technology, Hyderabad. He did his Bachelor's of Engineering in Electronics and Communication from Mufakhamja College of Engineering and Technology. He then pursued his Master's in Microelectronics Engineering for RMIT Institute in Melbourne, Australia, and PhD in Analog VLSI Design in 2015 from JNTU, Hyderabad. He has 19 years of teaching experience coupled with 2 years of industry exposure. A life member of IETE and an active member of IEEE, he also holds the prestigious role of Secretary for the IEEE New South Wales Section, Australia. With his vast expertise in the field of electronics and communication engineering, Dr. Arif is here to share his knowledge and insights with us today. Now I welcome Dr. Mohammad Arifuddin Sohail sir to take over the session.
Very good evening to all the participants. At the outset, I would like to thank the organizers, Manu, Ms. Hajra Fatima, Dr. Yusuf Khan, and all the other organizers for giving me this opportunity to be able to share some information that I've got with all of you. Pardon me for not sharing my camera. It's 11:30 p.m. in the night here, and I feel it's better that I don't share the camera. Can I get the sharing rights, Hajra, for sharing my presentation, please?
Yes, sir. You can share the presentation.
Okay. I hope you're all able to see my screen.
Yes, sir.
Okay. So before I go ahead with my presentation, I'll just take a few minutes to talk to you about my organization. It's customary that I would like to thank my organization for giving me this opportunity, to represent it and be able to speak before you. The company for which I work is called Advanced Communication Electronic Systems. It has been established 30 years back in Saudi Arabia with 60 plus offices and 4,000 plus employees. We have a current business of 3.5 billion Saudi riyals, and we are predominantly into the telecommunication sector. These are all our clients. All the Saudi government entities are our clients for which we work for. Our company is further divided into 4, and I have the privilege of being associated with all the 4. I work in all these 4 domains. Aerial solutions is with respect to drones. So I work with image processing using drone footage for oil and gas, Saudi Aramco. Then ACES India is into neutral hosting, telecommunication. ACES neutral host is into optical fiber communication. And ACES defense is in radars. So with my experience in electronics, I get an opportunity to dabble with various current technologies. These are the various departments, portfolios. Neutral host is one of the biggest business that we have got. We are the licensed operators from CST, and we do internal telecommunication networks for buildings, arenas, indoor and outdoor. We have the technologies of IBS, DAS, small cell, and private networks. This is our footprint. We are present at different places in Saudi Arabia, and in India, we are available at 6 different places. These are our success stories. The Grand Mosque at Mecca and Medina. We have our network at these places and all the other important places like airports, metros, and financial district and all the other things. Within India, we are present at Mumbai Metro, the network at Mumbai Metro, Bangalore International Airport, Surat Diamond Bourse, Agra Metro, and the upcoming Noida Airport is also from our side. Riyadh Metro, which has recently been launched, is completely the internet Wi-Fi is provided by ASUS, and we work with smart solutions. In fact, the first smart city in Yambu from Saudi Arabia, we were the one who deployed the complete smart city solutions. And I don't want to tell you what smart city solution is all about, but we did everything there. We do integrated security. It's not just the physical security. We talk about the security at the digital level as well. And we have the security at all the important power plants in Saudi Arabia. The latest business that we are into is data centers. So we build, construct, we do the cooling systems, power distribution, redundancy, and we build grain data centers. Currently, I am dabbling with multiple projects which involve migration of on-prem to cloud infrastructure. So we are heavily into data centers. A few examples of the data centers that we are building in Saudi Arabia. And our regular business is managed telecom services. So we cater for STC, Mobile, and Zain. Just like we have Reliance, Airtel, we have got STC, Mobile, and Zain. So this was a brief introduction about my company. It just took a few minutes for that. And I work as the research head for this organization. Now, let me talk to you about, I'll go full screen. Let me talk to you about the energy harvesting for sustainability of low power electronic devices. And I want to actually narrow this down to wearable technology. So basically, these are the topics which I will be covering on. Let's talk about low power wearable devices. Anything that you wear starts from shirt, pants, shoes, socks, watch, glasses, rings, smart finger, GPS, baby control, belt. All of these devices are smart devices. Nowadays, you can get electronics into all these devices. The big issue is, how are we going to charge these devices? How are we going to maintain the battery into them? And that's exactly what I'm trying to discuss in today's presentation. Energy harvesting for all these low power devices. I will also briefly touch upon medical devices. You will come to know the reason why. Medical devices like, which monitor blood pressure, pain management, hearing aid, enuresis, vital signs, remote patient monitoring, all these medical devices are very, very important today. And where are they located? The wearables right from head to toe. On the head, you can have immersive infotainment helmets. In the ears, you have headphones, hearing aids, earphone trackers. Eyes, you have got smart eyewear, AR, VR, glasses, smart contact lenses. On the body, you've got smart clothing, patches. On the arms, you've got medical smartwear, arm-worn trackers, skin patches again. On the wrist, you've got smartwatches, wrist-worn fitness trackers. Legs, you've got smart footwear. As I just said, shoes and socks. And I'm not even touching the implantables, which are inside your body. And all of you know very well about the pacemaker, which is an implantable device. I'm just going to talk about what we wear externally. And why did I discuss the wearables along with medical devices? Because we are going towards a synergy of both of them. You can see that the consumer electronic companies like Samsung, Bose, Apple, Fitbit, these are all into wearable devices. But now these companies are collaborating with health and medical devices like Philips, Medtronics, Omron, Starkey, and together they are building wearable medical devices. All of you are very well aware about the Apple phone, the Apple smartwatch. But when Tim Cook was asked, what do you think would be the single greatest contribution of Apple? He said it will be in the area of healthcare. So Apple in healthcare, that's what is the biggest contribution. And we have got multiple things happening in the healthcare domain. And let's just briefly touch upon the growth of wearables. From 2015 to 2026, you can see that the industry has grown like anything. From $20 billion US, it has grown to $160 billion. And the number of units are around 5 million units. And there is exponential growth as such. Growth of hearables and wearables. So frankly speaking, when I say we have got wearables, probably back in 2018, there were about 180 million units, of which a significant part, around 19%, was 33 million units of hearables. People used to wear a lot of hearable devices in the ears. The market has increased at a compounded annual growth CAGR rate of 20%. And it is now at 453 million units. Not now, like at least a couple of years back. And substantially, there is an increase in the hearables, which is 158 million units, 36% of the market. You can see that each of these devices, smartwatches, clothing, earworn, wristbands, sports watches, everyone has increased. And I want to discuss with you in today's presentation what is going to make this more exciting. 453 million devices are there. How are you going to charge them? How will you replace the batteries for these many devices? What is going to happen with the 453 million batteries? They have to work every day, every week, month, and year. How is that going to happen? Please think about it. Every one of you have at least 1 or 2 phones. You've got a laptop. You've got probably an iPad or a desktop or whatever. You may have a smartwatch. Men may have trimmers. Everything needs to be charged. And frankly, we are so busy in our day-to-day routines that we forget to charge things. And if you forget to charge our mobile phone, then it's havoc, it's terror. All right. How are we going to end up charging so many devices? Let me talk to you about the battery strain in only one device, which is a clock, a watch. The first one that you see here is a wristwatch, a normal wristwatch. And what is happening? It has only a 7-segment display with numbers. It has some basic watch functions, like you might have a small LED and a small alarm which will make a small sound. And it has a multi-year battery. Once you put a battery, it will go for 3 years, 4 years, whatever. And you go pay 50, 100 rupees and change the battery, and it keeps running. But does that happen with your Apple phone, Apple Watch, or any smartwatch? Do you think any smartwatch can last more than 3 days if you're using it regularly, wearing it on your wrist? Of course not. And you have to charge it. If you're not charging the watch, it is as good as a dud. You just have to throw it off. And what are the functionalities inside these smartwatches? First of all, the display will be very interesting. You have watch functions, of course, you will see time. You also have the motion and activity tracking, heart rate monitoring. You can find out how much is the heart beating with the small heart symbol. You have GPS in these watches. You can find out the altimeter, thermometer, and of course, Bluetooth. I mean, you know that you can take calls from these watches. The watch will ring whenever you get a call on your phone. So the watch is connected to your phone. So basically, the new functions inside the watch, apart from just displaying the numbers of time and date, is it has a cellular radio, it has sensors, and it has analysis and whatnot. So this is what is straining the battery, and the battery is going down every day. And for those of you who are from the background of electronics, and even if you're not, everyone knows that there is something called as Moore's law. What is this Moore's law? Integrated circuits, I mean the chips, the microprocessor chips. Mr. Gordon Moore said that the number of transistors, so these chips are made up of transistors, silicon transistors. The number of transistors in every chip is going to get doubled every 2 years. And you can see that the increase is like, 2 power x, keeps on increasing with respect to the timeline. The same is the capacity of the hard disk. A very high increase in the memory capacity. Very good. So we are increasing processing capability, we are increasing memory, we are increasing hard disk, but are we increasing the battery capacity? 6 years back, whatever was the battery, did we increase it by 20 times or 12 times? No, we did not. In fact, just for sharing purpose, I'm telling you that the number of transistors inside a Cerebras wafer scale engine 2 is 2.6 trillion transistors, which uses 7 nanometer FinFET process. This is a processor. Micron is a company. They have come up with a flash memory, NAND flash memory, and they have got 5.3 trillion floating gate MOSFETs. NVIDIA has come up with a GPU. How many transistors? 104 billion transistors. Just imagine. And that two of them. So totally 208 billion transistors inside the NVIDIA GPU. And of course, Apple. You use the Apple's devices. The Apple M2, 134 million transistors inside it. 5 nanometer technology. So this is increasing like anything. But what about the lithium-ion battery? No, it's not increasing. There is no Moore's law. There is no exponential increase in the battery capacity or whatsoever. You're still stuck up with the same battery, but you are expecting very, very high performance to support trillions of transistors. How is that going to happen? Okay, so let me discuss a little bit about an electronic microcontroller. You all know microprocessor, microcontroller. As I am an electronics and communication engineering background person, I will talk to you about that flavor a lot. So MAX 32620 is from Maxim Integrated. It is an ARM Cortex M4 microcontroller. So basically, this is the processing part, the heart of the chip. Apart from that, what else have you got? You have got a pulse oximeter, a heart rate sensor inside it, a 3-axis accelerometer, a gyroscope, barometric pressure sensor, a clinical grade temperature sensor. You can even connect this to ECG channels and monitor the ECG of a person. There is a HR heart rate detection algorithm running onto it. Of course, you'll have the flash memory and the Bluetooth and the ultra low power management IC. You can connect it with a USB Type-C, and all of these many things have to be supported by a small coin cell battery. Just imagine. How is this going to happen? Each one of them, how much power is going to be consumed by each of these devices? And how is this battery going to support this much power? And even if it does, will it last for a few hours? And then you will put it on charging again, and then you take it out and use it again, you will put it on charging? No. What is the solution? I'm taking you towards that. Just briefly discussing about the variable power budget. As I just mentioned, the most important component inside any wearable device is the microcontroller unit, radio, sensor, display, and power management IC. The other parts are also there, but let me just talk to you about each one of them. The maximum power that will be consumed will be with the display, about 10 to 100 milliwatts. The processing unit will be 0.1 to 10 milliwatts. Radio, when I say radio, I don't mean radio, I mean communications. How is this chip going to communicate with your mobile phone or your internet, IoT, and all that? 10 to 30 milliwatts. Heart rate monitor, very less power consumption, 0.1 to 1 milliwatt. GPS receiver, 10 to 100 milliwatts. And power management unit, every chip or every small device will have a power management unit, which will itself consume 10 to 20% of the entire system power. So I have put the numbers in front of you, and please bear in mind, you have to ensure that you get this much power from somewhere or the other. What is the source? How are you going to get it? Okay. You'll say, no, let me try and reduce. Okay. How? I'll reduce the power consumed by the CPU. So a slide on that. What we will use is the FinFET architecture. All right. Nowadays, all the chips that are coming FinFET based. All right, consume very, very less power. Apart from that, we are also reducing the power. Instead of giving DC power, we are giving pulse width modulated power. Instead of giving 1.2 volts supply voltage, we are reducing it to 0.3 volts supply voltage, which is called as subthreshold circuit design. It operates below the threshold voltage of the transistor. And if you reduce the voltage operation, what is going to happen? All of you know very well that the energy is half CV square. If you don't, let me tell you, the calculation formula for energy is half CV square, energy stored inside a capacitor, and all these are capacitive structures. So energy is directly proportional to the square of the supply voltage. If you're reducing the supply voltage from 1.2 volts to 0.3 volts, you can just imagine how much less energy you are consuming, because it is dependent on square of that. So that's how we will reduce the energy consumed in the microcontroller unit. Now, let me talk to you about the radio and display energy problem. When you say radio, I already told you, we are talking about Bluetooth devices. So Bluetooth low energy. Bluetooth low energy, BLE, works in two modes. All of you have Bluetooth in your phones. You have Bluetooth in your headphones. Everyone uses headphones nowadays, Bluetooth enabled. They work in two modes, sleep mode and active mode. They consume 2 to 10 microampere current in the sleep mode, idle mode. And when they are active, they are working, they will consume between 10 to 30 milliamps of current. All right. And you say power, multiply that with the supply voltage, whatever you're running it on, you will get the power consumption. So the power consumption is reduced to the order of microamperes here in the sleep mode. Let us talk about displays. When I say devices, of course, I'm not going to talk about the 55-inch TV display. I'm going to talk about very, very small micro displays. I mean, the biggest display that I talk is the display of a watch for you. I'm not even discussing, your mobile phone screen size. So I will say a 0.13 inch square micro display, a very small display. Where will you use it? You'll use it for augmented reality and you'll use it in smart glasses. This micro display delivers up to 10 million nits of brightness. So the unit of brightness for this display is nits, N-I-T-S. And how much power does it consume? Just 60 milliwatts. Just imagine a display that consumes 60 milliwatts. And this is purely based on micro LED. This is the emerging technology. All right. A full big screen of a micro LED display will consume just 1 watt. A 55-inch TV of micro LEDs will consume only 1 watt. All right. So basically, we are reducing the power consumption in display. We are reducing the power consumption in radio. We are reducing the power consumption in microcontroller units. Even if you have reduced this power consumption, what have you done to the battery? I am actually taking you towards the technology where you're totally getting rid of the battery. I am showing you 3 devices here on the screen which do not have a battery at all. These are battery-free wearables. You can see Matrix Power Watch. It's a watch that will run body heat, solar energy. Now you may feel, oh, my calculators have been there for 20, 30 years and they are working on solar. What's the big deal of this watch working on solar? Fine. Let's neglect that. You can see a very small UV alert device. What is a UV alert device? It is going to just tell you the intensity of the ultraviolet rays falling on your screen. This was developed by NW University, Illinois. It is working without a battery. And the last and a very interesting one is the Infineon NFC payment ring. So all of you know very well that we can tap a card. We don't have to insert the card in the POS machine. Nowadays, you can even tap the cell phone, the mobile phone, because the card can be loaded inside the phone, and you can simply tap the phone and the money will be deducted. But tapping a ring, amazing. All right, this is called as the payment ring by Infineon. You know what is the technology? The near field technology. Then in the ring, is there a battery inside that ring? No. Then where will it get the power from? It gets the power from this POS machine itself. The near field technology, which is going to connect these two, it will collect the power from that itself, and it will turn on. All right. So it is going to feed the power from the device which is serving. Amazing. So let me now talk to you about what are the feasible sources of ambient energy. What I am trying to tell you here is, when I say battery-free wearables, I am telling you we are moving towards technologies wherein we will harvest energy. As you remember, the topic of my discussion is energy harvesting for sustainability. So I am going to tell you that we are going to harvest energy from our environment. How will we generate this energy from our own environment? What are the various sources? Please remember, energy can neither be created nor destroyed. The entire mankind together cannot create a microwatt of energy. All they can do is convert one form of energy into another. That is what it is. So what are the various sources? Photovoltaic cells, of course, solar. Everyone knows amorphous crystalline solar cells are there, which are the best source of energy. And I know there are a lot of speakers who have already talked to you about renewable energy. They must have covered these aspects. But frankly, the difference between my presentation and what is being presented by all the others is that I will talk to you only about milli and microwatts. I'm not going to talk to you about kilowatts or megawatts at all. Just excuse me, I'm drinking some water. Sorry about that. So we have photovoltaic solar cells, amorphous and crystalline. We have vibration-based energy harvesting. And of course, when we say vibration, we talk about piezoelectric devices, which can be capacitive or inductive. We can generate energy from radio frequency. All of us are surrounded by mobile waves. You would never go into an area or region where you are not getting mobile signal. So wherever you are getting a mobile signal, can you convert that mobile signal into energy? Can you convert that into electricity? Interesting. Let us see. We have thermoelectric conversion. This is a very, very happening thing. Of course, human power, wind, pressure. I'm not talking on human power, wind, and pressure. I will be talking about the first four, just briefly, a couple of slides on each one of them, for you to understand what we are going to generate. But before that, the concept of power density. What is the meaning of power density? It means that per square, not meters, centimeters. Just imagine centimeter. Hold a scale in front of yourself, 1 centimeter by 1 centimeter square. If you have a solar cell and you leave that 1 centimeter by 1 centimeter solar cell in the outdoor, directly under the sun's exposure, you will get 20 milliwatts. If you put a piezoelectric sensor in your shoe, you might end up getting 330 microwatt. Vibrations from microwave oven, the microwave frequencies will generate about 116 microwatts. And you can see the other entities are centimeter cube. What is the meaning of centimeter square and centimeter cube? Some are volumes and some are areas. All right. So thermoelectric at 10-degree difference of temperature is going to generate 40 microwatts. Radio frequency GSM 900 megahertz frequency band will give you 0.1 microwatt, and Wi-Fi. Everyone wants to have Wi-Fi, right? We are all sitting in Wi-Fi zones. Right now, my laptop is connected to the Wi-Fi, and that's the reason why I'm able to speak to you. But this Wi-Fi signal itself can be converted into energy, and it can generate 0.01 microwatts per centimeter square. Okay, so how is that happening? Let us see. It's all happening because of transducers. Probably other speakers might have touched upon transducers. So I'm just going to very quickly talk to you about that any non-electrical input will be falling on a sensing element, and that sensing element will be given to a transduction element, and we are going to get an electrical output. That's what is a transducer. Converts non-electrical physical form of energy into electrical energy. So what's happening with this energy harvesting system? In the previous system, this was an open loop system, but I prefer closed loop things. So let me talk to you about the transducer, the variable device, and in between, I have kept a red block, which is called as a DC-DC converter. You will all be surprised to know that whenever I am talking about low power devices, I am not talking about the supply of 220 volts AC signal. No, no way. I am talking about only DC power. So all the batteries that are there are pure DC. None of them is AC. All right. So how do you take this DC value, one DC value, and convert into another DC value that is required? That's happening from something called as a DC-DC converter. And that converter is controlled by a PWM, a pulse width modulated controller. All right. And I'm going to briefly discuss how this is happening. All right. So this is a complete energy harvesting system. So if you want to sustain a variable device, a low power electronic device, you need an energy harvesting system. And the heart of an energy harvesting system is what? A DC-DC converter. Okay. So as I told you, I will be briefly touching upon various thermoelectric energy harvesting devices. Okay. So first and foremost, what is the principle of working of these thermoelectric devices? It is called as Seebeck effect. We have studied this as fundamentals in our engineering and even probably at the school level. But we are applying this now to generate energy. If you take two metal wires, dissimilar metal wires, they should not be same material. You should take two different metal wires, metal 1 and metal 2, and you keep the junctions of this at two different temperatures. All right. At one side of it, you heat it, and the other side, you again combine this and you place a multimeter or an ammeter. You will see current is flowing. All right. So it says that if you have two different layers, metals or conductors at different temperatures, then current is going to flow. This is the Seebeck effect. And you can see how small these thermoelectric power generators are. And they are getting or generating their heat from the human body itself. How that is happening? Let me show that to you. You can see about 1.4 microwatts per centimeter square of power can be generated using at a 5 degree Kelvin temperature difference. And let me tell you that thermoelectric energy harvesting, TEGs, is not a new concept. It has been there for like 20 years. In 2004 itself, the TEG, low power wireless sensor node, was introduced. And it was generating 200 to 330 microwatts at a temperature difference of 20 or 22 degrees Celsius. Now, where is it going to come from? As I told you, it will come from the human body. So if we are sitting and doing nothing in an AC environment, then probably we are generating about 100 to 150 microwatts, because our body, we are warm-blooded people. Our body normally is hot. And if we start walking, running, jogging, exercising, then our body temperature is going to increase. And because the temperature has increased, the temperature difference has increased, you can generate up to 500 to 700 milliwatt using the thermoelectric generators. That is great energy harvesting from only the temperature of our human body. A couple of slides on photovoltaic energy harvesting. All of you know solar panels, how they work. Photons will fall on the semiconductor material of PN junction diode, and it causes electrons and holes to move from the anode to the cathode. And that's what is the generation of current. I mean, we have been working on these solar panels for ages now. But I am talking to you about micro-sized solar panel. This is a $1 coin on which I have placed a SIMBET Ener chip. Ener chip is an energy chip. You can just see how small it is in size. It is already a product in the market. And what all are the things? If I just blow up that image into a bigger size image, you will see that there is a wireless transceiver sending and receiving signals. There is a solar cell which is going to charge this. So this will not have a USB-C cable charger or anything. Nothing will connect to it. It will automatically get energy from the environment. You have an inverter, you have sensors, you have MEMS pressure sensors. All right. All this together is existing and it is called as SIMBET Ener chip. Now, the third thing, in fact, I want to talk to you about is radio frequency. How can you generate electricity from radio frequency? And it is already happening. All right. Powercast is a company, and you know what a beautiful representation of this. Can you see that this is Wi-Fi signal or communication signal? This is how we represent signal, right? So this green energy, which is all around us, is being converted into plug, which is electrical energy. All right. This is by a company called as Powercast. They convert radio waves. How can they do that? These radio waves are nothing but, you could say, sinusoidal kind of waves. They will fall on an antenna. And I think every one of us know how an adapter works. How does a power adapter work? You will have an AC signal coming in, and that AC signal is given to a rectifier bridge circuit, diode rectifier bridge circuit, a transformer and a diode rectifier bridge circuit. Exactly the same thing is going to happen here. The AC signal from the radio wave is going to fall on the antenna, and then it is converted from RF to DC conversion. Then the power is conditioned and given to the output load. What is there in RF to DC converter? Same things. You have got 4 diodes, which is going to form the bridge structure, and you will have a capacitor and you have a load. All right. What is the difference then? This is working on 900 megahertz for cell phone signal. It is working on 2.4 gigahertz for Wi-Fi signal. So you are generating power or electricity from cell phone signal and Wi-Fi signal. All right. This is a 3 chipset Powercast energy harvesting circuit that you can see here. Very, very small in size, 1.3 centimeter square. All right. And it generates from 2 volts to 5 volts. All right. It works on a frequency of 1 megahertz to 6 gigahertz. You know what is the frequency of our power adapter, your laptop charger? 60 hertz. Because that's what is the AC signal coming into our home. And what is the AC signal coming here? 900 megahertz, 2.4 gigahertz. Very, very high frequency AC. So that has to be converted. That RF signal has to be converted into a DC signal. Okay. So that's a radio frequency transducer. Next is a MEMS vibrational energy harvesting sensor. What is the principle of MEMS? Micro electromechanical sensors, MEMS. This is on the principle of a cantilever. Cantilever is nothing but, I mean, you can imagine that there is a rod which is fixed at one position and which can be moved at another position. So it is just that on this side of it, this is fixed, held, and on this side of it, if you move it, vibrate it due to some mechanical energy, this piezoelectric crystal is going to get pressed, and when it vibrates up and down, it generates electrical signal. All of you know very well that piezoelectric crystals can convert electrical to mechanical energy and mechanical to electrical energy. So those of you who are in hardcore electronics, they know that all the oscillators, signal generators will have piezoelectric crystals in them. The reverse is also correct. So MEMS sensors, which can be put inside the shoe sole, it can be put inside the socks. These have this kind of a very, very micro cantilever mechanism, and we can generate power from them. In fact, Bolt is the name of the company, which is generating 3.3 volt DC and about 1 milliwatt of power, 0.1 to 1 milliwatt of power. These devices are already there in the market. Micro power generators is what they call. And I have covered these 4 for you. I have talked about thermoelectric. I have talked about photovoltaic, the solar. I have talked about radio frequency and MEMS. Let me now compare all these 4. All right. So if you look at the energy density, you will see that the lowest energy density is for the RF power. You know, from the cell phones and from the Wi-Fi signal, it's the lowest energy here. The next one is the vibration, piezoelectric. You can see it's in the range of about 10 microwatts, goes up to 300 microwatts. And these piezoelectric can be either piezoelectric, electromagnetic, or electrostatic or capacitive. Okay. Then we have got thermoelectric generators. Thermoelectric generators are in the range of 10 to 100. And finally, we have got solars, which vary from 1 to 15,000 microwatts. All right, 15,000 into 10 to the power of minus 6, you know, is going to be 0.15 or 0.015 watts. Okay, so this is the, you could say, harvesting, energy harvesting comparison of all of them. So what will you say? Okay, I will use solar, that's the best. But the question to you is, do you have solar available all the time? What if during the night you want to charge your watch, which is running on solar? There's no sun. You'll say, I leave the light open. Can your watch charge from the light that is there from the room? Yes, it may, but very less. And why will you leave the light open, switched on, while you're sleeping? So you want, while you're sleeping, your device should get charged automatically. So solar is not always the best option. In such cases, we might have to go for the other options like thermoelectric generators, piezoelectric generators, or RF generators. Okay. After discussing these 4, I wanted to talk to you about a little bit of theoretical concept, which is called as the maximum power point tracking, MPPT algorithm. Now, everyone in electrical engineering, electronic engineering, or with the engineering background will know the maximum power transfer theorem, in which it is said clearly that maximum power will be transferred when the source resistance is equal to the load resistance. RS is equal to RL. All right. And this is one particular point when RL and RS will become equal. So RS is equal to RL is a point where you can say it's 1 here. RL by RS is 1 means RL is equal to RS. At that point, maximum power will be delivered to the load. Okay. So this calculation of the maximum power point tracking is very, very important. All right. So I have talked to you about the different types of energy harvesting, calculation of memory power, MPPT. And now I will finally take you towards energy storage. So all this power that is getting generated, you can use it immediately or you can store it to be used later. There are two ways. You're getting some power, immediately use it. Power up an LED or power up a microprocessor or whatever. Or you can store this energy. I have seen the schedule. Some of them, one of the professors have already talked to you about energy storage devices. But I'm sure they must not have talked about very low energy storage devices like what I'm going to discuss now. Okay, so these very low energy storage devices, how are they going to work? Probably on radiation, chemical, electrical, temperature, kinetic, whatever. So let me show you that the energy storage devices, especially lithium ion, LiPo, NICD, NIMH, all these batteries, slowly are getting drained out. Okay, Tesla, BYD, these are the cars that are electric in nature. The entire car chassis or the bottom floor is full of batteries. All right, and they are guaranteeing about 7 years of battery life. After that, the battery will lose its efficiency and you have to change the entire floor. Costs about $15,000-$20,000, I'm telling, but it's as good as getting half the car, because the entire car, electric car, is working on the principle of these batteries, and these batteries will automatically wear out and they will lose their life. All right, so when I say these storage devices, we have to do something to improve our storage, which could be ultra capacitors, micro supercapacitors, fuel cells, heat engines, so many different options. All right, so we can see here that in-chip semi capacitor, supercapacitor technology enables storage energy of 0.2 joules. All right, 0.2 joules can be stored inside this capacitor. All right, back to our max 32620. You can see a lot of components here. I'm just keeping this as a reference for you, just for you to understand that the power requirements inside this are first and foremost control. Control means microprocessor, which is the ARM M4 Cortex, ARM Cortex M4 series. At the top, you can see this is the brain. This is the sensor. I'm just trying to give you an example of human body. This is the sensor. So you have got your eyes, ears, nose. So you've got your sensors here, ECG sensor, temperature sensor, whatever sensors. Then this is communications. It takes energy for you to speak. It takes energy for you to listen. That's what you do, communication. Or you want to signal someone by hand, come here, go away. That will also take energy, moving your hands. All right. So that is communications. Bluetooth, low energy, and GPS are the options there. Then we have got the user interface, which is the screen. And that is very, very important, because where are you going to press the buttons on? So that's really very important. And finally, you want to see what's happening. And that is what is the display, or the LCD or OLED. And of course, I talked to you about storage because that's an integral part. And you will be surprised to see that each one of them is working on a different voltage. They are not all of them working on 1.8 volts. No. You have a 5 volt LED, a 3.3 volt analog, 1.2 volts digital. So the analog part is always running on a higher voltage when compared to the digital part. All right. Communications, it will run on 1.8 volts. Processor works on 1.8 or 1.2 volts. User interfaces on 3 volts. How are you going to get these 12 volts? All right. Display is requiring 12 volts. Where do you get 12 volts when you are giving 3 volts itself? This is where the DC-DC boost converter is going to come into picture. And I'm going to cover that up shortly. The architecture of the variable device. You can see that you've got your 5 volt or 3.3 volt adapter, which you will connect to the wall. Wall adapter means the adapter will connect to 110 or 220 volts and convert into 3.3 volts. All right. This is going to connect to what are all the devices? Your processor, display, LED, sensor, Bluetooth. You will see that for each one of them, there is a DC-DC converter. Can you see DC-DC boost, DC-DC boost, DC-DC buck? I'll tell you what is the meaning of boost and buck converters, but essentially you have to understand that whatever there is a block, it needs power and it comes through a DC-DC converter. Okay, and I'm going to just discuss very briefly what is the difference between a buck and a boost converter. Okay, so if you look at the block diagram of power management unit, you will see you've got sensors, RF transceivers, switches, boost converter, maximum power tracking, MPPT. That's very, very important. And your energy is getting harvested from where? From the sun or from temperature TEGs, or we have just studied from radio frequencies, whatever. This is the energy harvesting. And that energy is going to go inside the chip to run this chip. Okay. So what we have realized is that we need to at least understand very briefly what is a DC-DC converter. So if you are from electrical engineering, you have definitely studied DC-DC converters. If you are from electronic engineering, there is a doubt you have not studied DC-DC converters, because it's coming in power electronics and a lot of students or teachers, or it's a faculty development program, you have got teachers, you will not know about what is a DC-DC converter. There are 3 types: boost, which means step up, voltage increases; buck, which is step down, voltage decreases; and buck boost converters. All right. So what is inside the step up boost converter? You will see a very, very simple circuit. You've got a supply voltage, you've got an inductor, a switch, and your diode. That's a very simple switch mode power supply, SMPS concept for a DC-DC boost converter. Okay. So the essence or the important part for this is the inductor, all right, and your diode. So for every DC-DC boost converter, it is very, very important that you have something called as PWM, pulse width modulation. A PWM signal is required. This is how we are going to generate a PWM signal using very, very small components like CMOS design. Can you see all these small transistors? The top transistor is a symbol for PMOS and the bottom is a symbol for NMOS. All right, so this is what is a simple chip inside which we have got NMOSs and PMOSs, and it's a PWM based boost converter. You all have seen that a very important concept here is an inductor. You cannot harvest energy and use it without a DC-DC converter, and you cannot get a DC-DC converter unless until you have an inductor. And inductors are bulky in size, they are big. So what is doing? We are going to try and manufacture inductors. All right, make our own inductors. How? On a chip, if you are going to draw a coil, that will generate a small amount of energy. All right, so that is off-chip converters. Then we also need to understand that there are different types of inductors. Okay, what are the 4 types of inductors? Conventional, coupled square, coupled octagonal, and coupled square white traces. So let me just show you how an inductor can be made on a PCB board. You do not have to physically hold the inductor. All right, just you can see a conventional inductor, coupled octagonal, coupled square with wide traces. All right, so these are all the images of inductors that are fabricated inside a VLSI design chip. Okay, and how do you design the DC-DC converter? as I already told you, you'll use inductors, you'll use capacitors, you're going to use semiconductor devices, and we are going to monitor what is the loss of the energy after conversion. So conduction loss, gate power loss, dynamic loss, these may all typically arise. All right. And for each one of them, you have got a formula. Can you see that the formula for power loss of any device is already defined as CL plus CG plus CGP, VGS square F plus IL square D, which is duty cycle, times RDS on, plus 1 minus D into RDS on plus R. All right. So this is the formula for the power loss that can be gauged, which is very, very small. You can see the overall thing is very small. All right. So the upcoming cases, I have just given you a brief idea of how a circuit is made, how a DC-DC boost converter is made, what is there inside the complete power management unit, and how energy is getting harvested. And the upcoming challenges that you can see are, you could say, future challenges that of an embedded coach. What is an embedded coach? This is an interesting concept. If you are wearing a watch, it is going to sense your heart rate. Now, that heart rate, does it send every second, or can it take a decision on the watch itself by monitoring the data and then discarding it off? So everything is normal, you will not send a signal. If that you see that there is some kind of an abnormality, you will immediately send a signal. So what we are doing is we want the ability to process locally. We don't want to just take the data and send it out. All right. That is a very important channel. And the other is intelligent variables. You can use activities like, applications like activity recognition, skill assessment, gait analysis, all the different emotional recognition, like a person is smiling, angry, all that can be detected by making use of wearable devices. And a lot of neural networks, AI stuff is going into this, and you will need a lot of processors. So the future definitely is very, very challenging, and we are looking at wearable power management devices for energy harvesting and very low power consumption. That was the complete crux. I would just like to conclude by telling that the energy harvesting technologies are improvising a lot, and there are many different areas. In fact, a few of them are already covered here in your FDP. I have seen fuel cells is there, thermocouples are there, all right, photovoltaic is there. So there are different areas from which we can generate energy. But when we talk about low power, we will use very few selected avenues, and most of the world's energy in future will be generated using these energy harvesting techniques, and we will not be charging the devices, they will get automatically charged. That is what is the concept that I wanted to talk to you about. These are a few references, and I would like to close my presentation with that. I hope I was able to give something which you are able to understand. If there are any questions, I can take them now. Over to you, Hajar. Hajra, are you there?
Arif sir?
Yes.
I am Nida Yasmin, assistant professor at Mano. I have a doubt, sir. Sir, you have
Yes, please
shown
go ahead.
the formula of power.
Yeah, half CV square.
Yes, sir. Sir, in that, what is D?
Duty cycle.
Duty cycle of the input signal.
No, what happens is the power, voltage, we are not going to give a constant DC voltage.
Yes.
We are going to give on, off, on, off.
Yes, sir.
There is no need of completely giving on. If you give that, it means you will always continuously consume power. So give on, off, and that will give you on time by off time plus on time, total duty cycle.
Okay, sir, one more doubt. You have shown a circuit that included inductor and a diode.
Yes.
So, we are switching on, like on off. So
Yeah.
just to generate the AC inside the inductor. That
No,
is the reason, or then how the
no.
inductor will give us the AC, sir? Because if for the inductor, if we don't give any changing current, it won't work as inductor.
Yeah. So basically, this is the concept of a switch mode power supply, and we are going to switch the. There will be a switch that will continuously keep changing. All right. So we are not going to pass current through the inductor. I mean, like a DC, in which case it will behave like a short circuit. So inductor is going to store energy, and we are going to, yeah, Mr. Bashir, basically DC-DC boost converter is a little bit of a detailed concept which I may not be able to explain in this short duration. In fact, I had a complete video of how this operation is happening, but due to paucity of time, I will not be able to take it up. Perhaps you can look it up. You have a lot of YouTube videos also which give you how a DC-DC operation is happening, but it's important for you to understand.
Any more
Any other
queries?
questions?
Participants, if you have any other questions, you can please go ahead. So I take it as no questions further. Thank you, sir. Good evening once again. Good evening, everyone. As we conclude this enriching session on hybrid renewable energy systems, it is my privilege to propose a vote of thanks to our distinguished speaker, Dr. Mohammad Arifuddin Sohail. On behalf of Maulana Azad National Urdu University, the organizing committee, and all the participants of this faculty development program, I extend a heartfelt gratitude to Dr. Mohammad Arifuddin Sohail, sir, for your insightful and engaging session on hybrid renewable energy systems. So your session has not only enriched our knowledge, but also inspired us to explore innovative approaches to tackle energy challenges in today's world. We are truly grateful for the time and effort you have invested in preparing and delivering such a valuable presentation. Your passion for teaching, combined with your research and industry experience, has left an incredible impact on all of us. Once again, I thank you, Dr. Arif sir, for your invaluable insights, and we sincerely hope to have you with us again in future for more such inspiring sessions. Finally, I would like to thank all the participants for your active involvement and keen interest in the topic, making this session even more meaningful. Thank you, everyone. The participants.
Thank you so much for the opportunity. I appreciate that.
Welcome, sir. So, dear participants, we'll wait for 5 minutes. We'll have a break of 5 minutes, then we'll start off with the next session.
I'm going to drop out now, Hajra. Thank you so much.
Thank you, sir.